Okay. Hi, everyone. My name is Harry Goldstein. I'm currently a postdoc at the University of Maryland, but as Aaron said, I recently accepted an offer at the University at Buffalo, so I'll be there in the fall. I'm really excited to speak with this group in particular today because I know a lot of folks here are excited about testing, and that's what I do for my normal research. So my dissertation is titled Property-Based Testing for the People, and I did my dissertation working on usability and also performance of testing techniques. Um, but y'all have heard about property-based testing a lot lately. Aaron gave a talk on property-based testing a few sessions ago. Alp gave one just after that. And so rather than tell you again about a bunch of stuff that they already told you, I decided I would talk about something totally different today. So today I'm going to give a talk about language design instead, but if you want to chat about testing sometime, happy to do that. I want to give a few caveats and disclaimers about what this talk is and isn't. So this talk isn't to talk about my main research, as I just said. I'm almost coming at this as more of a hobbyist. I mean, my research area is broadly programming languages, but just keep in mind this isn't like research talk from academic. This is a talk from someone who really loves programming languages as a hobby as well. This is not a talk about proof assistance or theorem proving, even though proof assistance was in the title, and I'll get to that in a second. And this is not a ploy to get you to learn a new programming language. I mean, unless you want to, but like you don't have to. What this is instead is a talk about programming language design and about integrated development environments. And if it's a ploy for anything, it's a ploy to get you to realize that the programming languages that you currently use could be better. And the reason I care about this is because as programmers, languages are the way we interact with the world, right? Programming languages are the thing we have, the tool we have to sort of have impact. And the great mythbuster and maker, Adam Savage, in his book says that tools are the way you explore possibility space. Your programming language both enables and limits your thinking, your approaches to problems. And so it's really important that the languages we use aren't holding us back. So today I'm going to introduce you to a programming language if you haven't heard of it before. It's called Lean. And I'm going to tell you about two things I think Lean does really well. And hopefully you can take away from that some ideas for how the languages you currently use could maybe do some of those things better as well. So to get started, what is Lean? Lean was invented by Leo DeMora in 2013. Leo is at AWS now, and Amazon does fund some of Lean's development, but it's not really an Amazon project. Lean 4, which is quite different from its previous iterations, was released in 2021. So that's how I get away with calling this a new programming language. It's not a massive language. It has about 11,000 regular users on its Zulip. That's a lot, but not that much in the grand scheme of programming languages. But just so you kind of have a sense of the scale here. Lean is there's just a few things about sort of Lean as what it's like to program in it. So it's a pure language. If you're familiar with Haskell or Elm, you might be familiar with this kind of thing. The idea is if you want to do side effects like printing to files or accessing the network, you have to mark that in the type. So this function here, this average function, says it takes a list of floats to a float. Well, that can't possibly print to the terminal as well. This is not going to come up much in this talk, but this is an important feature of Lean and languages like it. Lean is also a functional language, which means that functions are the main way that you do abstraction and composition in Lean. But hopefully this is not too foreign to folks here. I mean, modern programming languages have anonymous functions, have functions passed around, functions that take other functions as arguments. This is not nearly as niche a thing as it was, say, 10 or 15 years ago, I think. And finally, Lean is strongly typed. And I mean like very strongly typed. Normally, a programming language might prevent you from using a string where you meant to use a float. But Lean's type system is so powerful that it can actually express and check mathematical proofs. If you've heard of Lean before, this is the context you've probably heard of it in. Lean is being used right now to formalize a large proportion of modern mathematics. There's a project called MathLib, and people are using the Lean language and its incredibly powerful type system to basically formalize mathematical theorems. The mathematician Terence Tao has been actually streaming on YouTube, writing Lean code, which is kind of crazy. And they're good streams. You should take a look. I think if you've heard of Lean, this is the context in which you've probably heard it. Lean brands itself as a proof assistant. However, my thesis for this talk is that Lean is not just interesting as a theorem prover. It's actually a really well-designed and modern programming language, and I think it has things that we should learn from it for the languages that we currently use. So let me start by talking about one of those really interesting things that Lean does, which is its approach to metaprogramming. Now, if you don't know about metaprogramming, this is the idea. One good definition is sort of writing programs that produce programs. But another definition, which I think may be more intuitive for the context of this talk, is writing code that changes how the compiler compiles code. You may have encountered metaprogramming before. If you've ever worked in a Lisp-like language, like Racket, for example, you do metaprogramming all the time in the context of macro programming. Rust also has macros, both multiple kinds of macros. And C++ has templates and other ways of kind of doing programming at compile time. And so here's an example from Rust. We've got this vecbang macro, which just initializes a vector. And the code, the vec code over there expands to this code, right? When you write vecbang123, you get the code that initializes a new vector and pushes the values onto it. And it's critical here that vec is not a function. This is not a function that gets called at runtime. This is an expansion, right? This code expands into this other code in the compiler. And so I'm going to talk about now how Lean does this, and we're gonna see some slight differences to how Rust does it, but that's the sort of basic idea you should have in your head. So here's some Lean code. This is declaring a structure. It has two fields, start and finish, and it's going to describe a kind of range of values. And you can construct this kind of value with standard range make, and then the lower bound and the upper bound. And suppose we want some nice notation for this structure, because we don't want to have to write standard range make every time. We want something that feels closer to the idea that we're trying to express. And so maybe we want this notation here, where you write open bracket, lower bound, colon, upper bound, close bracket. And Lean then would take that and compile it into the thing up top. And we don't want the Lean compiler authors to have to figure this out every time there's a notation that you want. We want the user to be able to say what this notation means. And so in order to explain how we can do this in Lean, I need to tell you a little bit about Lean's compiler. This is the kind of pipeline that Lean has for its compilation. You start out with code in your editor. Then you move into a kind of the parsing step turns that into a structured representation of the code. The elaboration step turns that into an intermediate data structure that the compiler knows about. Then Lean does something kind of neat, which is it compiles that to C code, and then it compiles the C code with a standard C compiler to an executable. Just an aside here, I think this is an interesting design choice. It means that Lean is very portable, right? Any language that any architecture you have a C compiler for, you can compile Lean code to, which is neat. And something you could think about if you're trying to implement a programming language but don't want to have to think about the portability story yourself. But we're talking about macros. And the thing you should be focusing on this slide is these two first steps, parsing and elaboration, because these are actually programmable by the user in Lean. And so I'm going to show you how we program the parser and the elaborator to get the range syntax that you wanted. So starting off with parsing, we write this top line in Lean, say syntax, open bracket, num, colon, num, close bracket is a term. And this is telling Lean, when you're parsing, if you see this sequence of data, then you can interpret that as a term in the language. And concretely, when the parser sees that string 0 to 200, it turns it into this tree, which gives a little bit more structure to that syntax. Now, all we've done so far is told Lean that this syntax is valid syntax. Now we have to tell it what to do with that syntax. And so that's where we go to an elaborator macro. And what this match statement here is matching on the particular syntactic form and saying, when you see n:(m), turn that into a call to standard range. And now in the compiler, during elaboration, it turns our syntax tree there into this internal representation of a function call in Lean. The key idea here is that the programmer can change the way that code is parsed and elaborated to strengthen the connection between concepts and notations. Right? If there's a concept in the sort of idea of ranges, you can now bring the notation closer to that concept. But if this was all Lean could do, I probably wouldn't be jumping up and down right now trying to tell you about it. Lean's the way that you can control the parser and elaborator is actually really powerful in Lean. So for example, here's that average code that I showed you before. But what if I told you that this is also valid Lean code? This looks like Python. You're initializing mutable variables. You've got a for loop that you're sort of summing up things in the loop, and then you return the result. But I told you that Lean was a pure functional language, which means it probably shouldn't have mutable variables and loops. And it really shouldn't have things like breaking out, continuing in a loop or exceptions, things like that. Like what's going on here? This is not this looks like it sort of reads like Python code. And the answer is that all of this is macros. Lean expands all of this when you print the definition to purely functional code. You can kind of have your cake and eat it too. You can have imperative syntax, which many people find more intuitive, while still having this kind of core functional language. And there's a lot of benefits here. The language doesn't need stateful references. It doesn't need for loops or continue. It doesn't need exceptions. It can just have metaprogramming, and users can build the paradigms they want on top of the programming language. So the takeaway from this part is that Lean's metaprogramming allows the language to stay simple while supporting different programming idioms and techniques. Okay. Now I want to tell you about the second thing that I think Lean does really well, which is live programming. Now, live programming is the idea that you can give the programmer immediate feedback on the output of a program as it's being edited, replacing the edit, compile, debug cycle with a fluid programming experience. And you've probably seen live programming before. Actually, if you use a modern IDE, you almost certainly have. Things like type information and documentation on hover, auto-completion, and jump to definition all fit my definition of live programming. And this is not unique to Lean. Plenty of languages have this kind of thing. And many of them, including Lean, support it through things like the language server protocol. The LSP is a protocol that defines how language tooling, like the compiler and the build system, should interact with the user's editor. And it was originally developed for VS Code, but it's now supported by pretty much all modern code editors. And the way this works is that you have a server provided by the language. So this is provided by Lean's build system. And then you have a client provided by your code editor, and and the two can talk about things like type information, where definitions exist, and things like that. Now, like I said, this is pretty standard right now, but Lean takes this all a step further. Because in Lean, this is a screenshot of a Lean editor, you have this panel to the right of your code called the info view. And the info view can show you things that are kind of more interesting than what you normally get from your editor feedback. So here's a simple example. We have Lean showing that the result of evaluating that code that I wrote over there is 2.5, right? And as I edit my code, because Lean is constantly recompiling the file, that number, that 2.5, will change as I add numbers to the list or something like that. And already this is like getting a little bit beyond what you can do in many programming languages in terms of kind of live feedback of what's going on in the code. But the way Lean takes this way farther is with widgets. So widgets are arbitrary bits of UI that can be injected into that info view during the elaboration stage of the compiler. In other words, it lets you use metaprogramming to enhance the live programming environment. This was originally designed for representing mathematical objects. So for example, here's a Rubik's Cube being rendered in the info view. But I'm going to show you a demo of some things that I think are a little bit more useful for like programming. So if I switch over to, okay, good. But I want to be able to see it on my screen too. There we go. Okay. So I wrote a ray tracer in Lean not too long ago. And as part of writing that ray tracer, I wanted to be able to view PPM images in my editor. So I didn't have to like switch out to a PPM viewer and back. And so here we're generating a PPM image. And when I click on this PPM command here, it renders this PPM image in the info view. What's actually happening is that this command is a macro that I wrote that runs at elaboration time. And it tells Lean, hey, I've got this PPM image, and gives it the JavaScript that it needs to render it in the info view. We can also see this lovely gradient. I didn't pull over any of the images I actually made in the ray tracer. It's a very slow ray tracer. But like you can start to see how this slightly changes the game, because now we're not just thinking about like text that we're rendering here. Now we can look at whatever outputs we want in whatever forms we want. And so now I can make good on the fact that I'm a testing researcher and show you some testing stuff that I did with this. So I do property-based testing as part of my work. And that involves randomly generating data to test programs with. So suppose I have this data generator, which is supposed to generate values between 5 and 10. Well, what if I want to validate the distribution of that data so I kind of know what it's doing during testing? I can click on this command that I wrote, and now we get a bar chart of the sampled data from the generator. And what actually happened here is the Lean compiler, during compile time, took my generator, sampled it 1,000 times, and built this chart, which it could then render for me in the info view. And I think that's pretty cool, right? We're now like able to just sort of view whatever we want over here. We can view distributions of lists. We can look at the proportion of lists that are sorted. This is maybe useful if you have a function that's supposed to take sorted lists as input. But I'm going to skip down here to what really blew my mind, which was this one. So this is back to just a distribution of numbers. But if I click on this little details panel here, I get 2 sliders. And if I drag this slider, the distribution changes. And actually, notice my code changed too. the number in the code changed when I changed the slider. I'll change the slider again and you can watch. And the distribution is changing live with it. So now imagine, right? You're tuning some machine learning algorithm. You're writing a video game and you want to mess with some variables, right? You can build arbitrary user interface elements for manipulating your code in Lean, and then just render them, and then it changes the code there. And none of this required forking Lean. None of this required forking Lean's extension or a new extension. This is all just built into the ecosystem. And so let me show you actually how this works, because it looks a little bit like magic. So remember, we've got the language client and the language server. There's also a widget server, which is hosting all those widgets that are appearing in the info view. And we've got the compiler. And what's happening is that during elaboration, we're registering a widget with the widget server, which renders that slider. The slider's onChange event goes to the language server, which tells the language client to issue an edit to the file, which then, when it persists to the file, triggers Lean to recompile the code and regenerate the charts. I didn't think this would be possible when I implemented this. I was like, there's no way they're going to let me do that. But they do. And I think this is like sort of fundamentally different from the way that you can program with macros and live programming in most other programming languages that I can think of. And yeah, so Lean's live programming support allows developers to like totally change their IDE experience without forking the language or the editor extension. And so now I want to kind of wrap up and bring us kind of all the way back up. So what should we learn here, right? Well, a metaprogrammable parser and elaborator mean that a language can be really simple, but still support complex idioms. You don't need to know when you're designing the language all of the things your users are going to do with it. Buying into standards like the language server protocol provides a simple path for new languages to build live programming features. And then combining metaprogramming with live programming means that users can build state-of-the-art interactions themselves entirely within your language ecosystem. And none of this is specific to Lean. None of this is specific to a pure or functional programming language, nor is it specific to a proof assistant, right? When people look at Lean as a proof assistant, I think they're missing the fact that like it's doing some really cool things as a language itself. And so I think that's what I want you to take away here. If you think that this kind of thing would be useful to you in your day-to-day programming, think about whether the language you work in could have these kinds of things in its ecosystem. I don't think it would be incompatible with most of them. I think that's all I have. You can see the Lean language here. This is my contact info, and I'm happy to take questions.
So I really enjoy the metaprogramming, and I use that a lot when I write Rust until I try to debug macros. So it's really, I don't know, it's because like I'm using it wrong, or it's just like really hard to debug macros. Like you don't really see how the programs are generated, and you don't, like, you can't really step in, and like when I was using it, Rust compiler doesn't really let me know what I think it has changed recently, but does Lean try to solve that problem?
Yes, so Lean gives you pretty good tools for inspecting the code that is generated by your macros and things like that. It's not perfect. This is a hard problem in terms of like helping developers to understand what's going on and debugging those things. But I think Lean is doing a pretty good job. There's lots of, and you know, because it's this very live system, you can do things like, you know, write your macro and then mess with it and test it and print it and inspect it just all right there in the file. Which I think, when I have been, most of the stuff I showed you today are like little macros that I wrote myself. And when I'm like writing and debugging these, I felt like it was a pretty good experience, or at least as good as what already exists.
So metaprogramming and macros are really useful. It lets you represent a lot of cool stuff that you couldn't otherwise easily do. But a problem I often run into in reading code that makes heavy use of it is, oh my god, this sucks. I have to understand how the macros work now. Do you think that is that same sort of problem, I guess, rampant in Lean because metaprogramming macros are so common?
It's a great question. So this is, I have definitely made that argument in the past. People will argue for this thing called language-oriented programming, where sort of for every domain you write your own little programming language in the language, and you sort of use that to solve your problem. And I do think that, like, when you overdo it, it absolutely runs into that problem where you're sort of writing unintelligible code to anyone else. I think in the Lean ecosystem, that is solved by people trying their best. So for the stuff with like for loops and stuff like that, I didn't implement that. That is implemented by the Lean team, even though it's not like built into the compiler. And I think that helps, like when it's like huge, big notational things like that. I think centralizing that effort is better. I think this is absolutely a problem, and sometimes the benefits of being able to sort of match your notation to the way you're thinking is worth that extra overhead. And also, like, Lean's macros have jump to definition and things like that. So if you don't know what this construct is, you can jump in the IDE to where it's defined. So at least that works.
Yeah. So are the macros only like syntactic macros, or do you also have access to like type information?
You have everything. You have it's not so there are macros which are syntactic, and then there's elaborator macros or elaborators. I forget exactly the terminology, but those have access to the whole Lean AST and can entirely rewrite it. Well, so the reason the historical reason for this is because when you have a proof assistant and you want to write a proof in a programming language, you do that by manipulating syntax trees. I'm not going to explain all of that, but basically you have tactics which manipulate some abstract syntax tree. And so all of that machinery gets repurposed in Lean for programming as well as for proving, which turns out to be just really powerful. Yeah.
You said that this could be done in a different language and you don't really need to rely on Lean's features. But like, don't you need the pure functional properties to be able to do compile time evaluations of object features? You don't want like side effects while you're evaluating your macro operation.
So I definitely think the safety story is much nicer in Lean because you have these things to fall back on. But lots of other languages, like C++ has a bunch of compile time programming and disciplines to figure out how to avoid doing side effects in those fragments. Like you do have to do some work to make sure that you're not doing something too gross at compile time. But I don't think it's like absolutely necessary for the language to be sort of this committed to pure functional, to being a pure functional language to make that work. Yeah.
You kind of said like at the beginning of your talk that maybe other languages were missing the boat, that like you wanted to convince us that we should try to do more of this.
Yeah.
Do you have like a thesis on like why they haven't, or like what sort of hurdles to the piece?
So I think part of it is that the technology to make this work is not that old. So like the language server protocol was not like the ubiquitous thing it was. It is now 5 to 10 years ago. And the metaprogramming story for Lean is part of a very, very long history of programming languages research on metaprogramming. And it just so happens that we're sort of at a point in history where we figured out a lot of the really hard parts to the point where we can do this in a nice way. So I don't necessarily think that like other languages that don't have these things were dumb when they made those original decisions. But I think that now that we've seen that a language that isn't even meant to be a programming language can do this kind of stuff, like I think it's time to catch up. Yeah.
So you showed an example of the widgets like editing your source code when you're playing with the sliders. How much of power do widgets have to like mangle your source code, and has that happened to you yet?
So I definitely I don't recommend developing that kind of widget unless you're prepared to think very carefully about it. I have not entirely ruined too many files that way, but it's definitely a concern. It's not like there are concerns there for sure. You have to be careful.
I'm just curious because you're about to start teaching, and I'm wondering if you think this interactivity will reduce some of the sort of bad habits that we see among students, like ignoring error messages, for example.
I mean, I definitely think a more interactive environment is great for education. I also think that I probably won't subject my students to a proof assistant as like an early language. So like, I have a vested interest in wanting this in languages that newer programmers are using too. But yeah, I mean, I think it's a double-edged sword. Like as folks have pointed out, like these are power tools. Like you can use these tools incorrectly. Very powerful metaprogramming can cause all sorts of problems if you're not careful. And so like, yeah, there's trade-offs here, but I definitely think some of the live programming features like really do change how beginners interact with the language.
So in Hazel, you can put the bits on top of the source code.
Sure.
Right. Do you have any comparisons between those things, like having it in a separate window?
Yeah. So I think
Making the file more than something that's text.
I think for me, it's a deal breaker if you can't use a standard code editor. And so like if VS Code does not implement dragging some bit of UI onto the code, then I don't want it, right? I want to use a code editor that has other extensions that I'm used to using. And so like for me, the info view is a nice middle ground.